Jai Hind everyone. My name is Gunjan. I am assistant professor in Ajay Kumar Garg Engineering College, Ghaziabad. I am taking subject design and analysis of algorithm for fifth semester student. The subject code is KCS 503. Today's topic is RB tree, or we can say red black tree. So these are the outlines for today's lecture. First, we are just brush up the what is the balance tree. After then, introduction about the RB tree. After then, the properties of RB tree, some rotations in RB tree, and at last the insertion process in RB tree. So let's start. Firstly, what is balance tree? In binary search tree can implement any of the basic dynamic set operation which is taking order of n time. These operations are order of log n if tree is balanced. Now, there has been a lot of interest in developing algorithm to keep the binary search tree balanced, including one is red black tree, ABL tree, split tree, and many more. Now, what is RB tree? As the name suggests, in this particular tree, every node containing two colors. Either it is red or it will be black. So, RB tree is basically a binary search tree in which each node is colored red or black. Contains on the coloring and connection of node ensures that no route to leaf path is more than twice as long as any other, so tree is approximately balanced. In each arbitrary node contains these particular fields. Every key contained is left subchild and the right subchild, obviously a color field and the parent. And this parent, obviously for a root node, this parent having a null address. Now, what is RB tree properties? Actually, in binary trees argumented with node color, operation designed to guarantee that the height is log n. RB tree is guaranteed to give the balanced solution in maximum 2 rotation and the height is log n. Now, these are some most important 5 properties we have to check after every operation. Maybe insertion is there, maybe deletion is there. These properties must be followed. If in operation, insertion or deletion, any property is volatile, then we have to fix them. So what are these properties? Number 1, every node is either red or black color. Number 2, every leaf, which we also call null node, having a null pointer, is black. We have to point, it means every real node has 2 children. Number 3 property, if a node is red, both children are black. So we can say no consecutive red node is acceptable. Property number 4, every path from node to descendant leaf contain the same number of black node. That means the node black, or we can say the height of black in every path should be equal. And the last one is the root is always black. Next is, in this particular slide, we are just going to check the properties if these trees are arbitrary or not. Let's consider this first example. Here I am checking all the 5 properties which I have discussed earlier. So just check the number of black. So if we are checking this particular path, then wait. Yes, if we are taking this path, the height of black node is 1. Here we are saying the black nodes are 2. Then the height of black is not equal in both the side. And the other one is we are checking the root having red color, which is actually not possible. root must be black and the height of black nodes in each the path is always equivalent. Now consider this question number 2. So the root is black. First property is cleared. After then I am going to check any red node. So by chance there is no red node. Is it possible in arbitrary? If red is not possible, exactly possible. We discussed every node should have a color red or black. No issues if any node of red color is there, no issue. But all the properties can be checked. So if here no red node is there, so the red parent and red child is also done. After then we are checking the balanced height of black nodes. So if we taking this path, so 1, 2, so black height is 2. If we are taking this path 1 and 2, if we are taking this path, then height is 2. But one another path is there. This to this. This is having only one black height, which is not acceptable in arbitrary. So what we are doing in these particular steps which are discussed earlier, we have to apply some fix up algorithm, just rebalancing them. Now consider this example. Here root is black, okay. Height of black, this is 1, this is 1 and this is 1. Now in this particular case we are saying the properties of arbitrary is going to be true, but we are again checking it is BST or not. We are also checked, right? So 10, in 10 the left child is 11, which is not acceptable, because in very first slide I also cleared arbitrary is a BST. So the property of BSTs are also fine. So the left child of any node is always a minimum or equal key, and the right child is always a greater key. So this is not a BST. तो यहाँ पे भी हमारी जो condition है वो volatile हो रही है. Now next. So this is the solution which I have already discussed. This is not a arbitrary because the root is red. This is not a BST because 11 is there, and this is also not a arbitrary because the black height is volatile. So if we adding any node having color black, now this is the arbitrary. Okay. This is another example. Let's consider this is arbitrary or not. Just checking all the properties. Yes, root is black. Done. Now, any red. This is the red node having a red child, which is actually not acceptable. So, this is not a arbitrary. One point. I want to tell one another thing. What is the criteria how we can add a node to be a children of any node? So what is the rule actually? If we are going to add, suppose this is having black color, okay? Now this is the arbitrary. Suppose if we are adding any node, suppose 1 is there and the color is maybe red, then the maximum path is 1, 2, 3, 4. The maximum path is 4. And we are checking the very close path. The very close path is 1, 2. The close path is 2 and the maximum path is 4. But this is the rule. This maximum or minimum, the relation of maximum and minimum node is not exceed to twice. As we see, the minimum path is 2 and the maximum is twice to minimum. which is 4, but exceeding this is not acceptable. What I'm saying, suppose the color of this node is 1. Now, suppose any 0 node, having 0 key, having 0 node, the color is whatever, but it is actually not possible because the path is 1, 2, 3, 4, 5, which is exceed to the twice property. And just check, if this is having black color, then obviously the black property, height of black should be equal in every path, is destructed. If it is red, then we are saying the red child and the red parent, which is again not acceptable. So in short, we are saying there is another formula. If we considering a maximum path and we considering the very smallest path, this relation is at max twice, not exceed twice. Now, there is some rotations which you have already cleared in AVL tree. Just go through about what is the rotations. So, let us take an example. Basically, rotations are two types. If we having some issue and we are going to fix up these particular issues, the rotation is required in RB tree as in AVL tree. So, what is the rotation actually? Just supposing this is the node Y and this is the node X, maybe some subtrees are there or maybe not. We have to apply the right rotate around with Y. So, this is the Y, and what we are supposed to do, we have to rotate this Y in right direction. So, if we are stretching this Y to right, then obviously this X come to the up. So, the position is that the X is going to up and Y comes down. What is not change? When we are stretching this X to up, the A remains same. A previously as a left child of X and after then again a left child of X. What is not change? The C. When we are stretching this Y to right, then this C, which is previously a right child and after then again it is the right child. No change in A and C after the rotation. But what happened to B? Because when we stretching Y to down, this Y comes to at right of X, as I am showing here. This Y becomes the right of X. Then what is done with B? B is now becomes the left child of Y. The properties remain same as we are seeing. B is the right child and in this particular solution, B is again a right child. So, this is the solution of rotation. If we are going to rotate any node around any node, this steps involved. What happened in left rotation? Just follow the opposite direction. We are taking as a example and this is the solution. How? We are doing left rotate around the X. This is the X. We are going to do left rotation around the X. So, what happened? If we stretching X to this direction, what we are doing? We are rotating X at left. Though what has happened? X stretched to down. What does not change? The A, which is the left child after the rotation, again it is the left child of X. And when we are stretching to X down, the Y node obviously move up. And what is not change? Again the C. which is the right child, and after the rotation again it is the right child. What is the changes? Actually, when we are stretching this x down, then y becomes as a parent and x become as a left child of y. Then the left child of y becomes the right child of x. This is the solution of if we are doing the right rotation or we are doing the left rotation. So there is a algorithm. So there is the algorithm. This is the standard algorithm. By using this algorithm, we can say the rotations are performed. Okay. So as it is the right rotation. Next this is the question. Now we are starting or we are going to the insertion operation in RB3. So in the university examination, this is very important question. This question having the maximum marks in your university exam. So this is very important. What is the question outlook? The question is maybe it given you a random data and say create a RB tree. So I am taking random data like 10, 18, 5, 4, 15, 17, 25, 60, 1 and 90. What are the steps? So these are some steps. Basically this is not a exact algorithm. In next slide I am going to exact algorithm. This is the simplest way for representing the insertion algorithm. Okay. So what are the steps? If tree is empty, then create a new node as a root node with color black. Initially the tree is empty. So what we are doing? We are just creating a node, give them the key value and the color is black. The color is black. Okay. What is the point number 2? If tree is not empty, then create a new node as a leaf node with color red. Okay. So in step number 3, if parent of new node is black, then exit. So parent of this node is what? This is the very first node. And parent is what? Parent is nil. And in starting, I also say the nil color is assumed as black. So if parent of new node is black, then exit. Then after insertion of this 10, exit. Up next to the node 18. So again checking these steps. So if tree is empty, is tree is empty? No. Tree is not empty. Some nodes are there. Then step number 2. Step number 2 is if tree is not empty. Yes, tree is not empty. Then create a new node as a leaf node with color red. So 18 is going to be a leaf node or a child for this particular 10. And which child? Which decide BST property. So 18 is greater than 10. Obviously, it becomes a right node and having a color red. And every insertion or every deletion, we have to check all the properties, mainly these 3 properties. Root is always black, no 2 adjacent red nodes, and count of black node in each path. Then every 3 properties are cleared in this particular situation. Root is black, no red child parent, and the black height is same in both the path. Now the next element is 5. So 5 is less than 10. Obviously it comes to left of 10 and the color is red. So all the three properties are going good. No rotation, no case matching is required. So if parent of new node is black, so new node is 5 and the parent is black, then exit. The next node is 4. So again checking, now tree is not empty. In next elements, I am not going to check the first point, first step. We are directly execute from the second steps. So tree is not empty, create a new node as a leaf node with color red. But which parent? The 4 having the criteria inserted at the left of the 5. So 4 is here and color is red. Now checking step number 3, and step number 3 is saying if parent of new node is black. So new node is 4 and parent is 5 which is having color red. Then case number 3 is not exist. We are going to case number 4, and case number 4 is if parent of new node is red. Yes, the parent of new node is red exactly. Now what we are going to check next? Then check the color of parent's sibling. So new node is here and the parent is here and the sibling is this 18. Just checking both the colors. If the color of uncle is red, just go through the point number A first. If the color is black, so color is not black. Sibling's color is not black. So step number 4B, what is saying over here? If color is red, yes, color is red. Then also check the parents to parents which is not a root node. So firstly we have to do, if color is red then recolor. Means parent and uncle, just do recolor. So it becomes black. Right? What is the step? Next step, also check if parents parent of new node. What is that? New node parent of parent is not a root node, but in this case this is the root node. So exit. Now what is the next node? Next node is 15. Now again tree is not empty, create a new node of color red and add accordingly. What is the place for 15? The 15 is greater than 10 and less than 18. So the place is here, right? And the color is red. So no properties is volatile, every properties is fulfilled. Now the next number is 17. So what about the 17? Which is greater than 10 and less than 18. So go through the left subtree and 15 is there. 17 is greater than 15. So it becomes a right child having red color. Now in AVL tree, just recall the AVL tree. Which type of rotation is required? As see, first thing is which is volatile, the arbitrary properties, and which property? No two adjacent red node, but we having two red node in a adjacency, right? So here the rotation is something is adding to left to right, means LR rotation. What is the solution of LR rotation? First we are going to do a left rotate, after then the right rotate. So what is the solution? When we are doing left rotate, then 17 at here and 15 is here. What are the color? These are the color. This is the left rotation. After then the right rotation. Then what is the answer? The 17 becomes a root. A 17 becomes a root. So this is the 17 and becomes a root, and 15 is the left child and 18 becomes the right child. So what is the final result? It is 10, 5, 17, this is 4, 15 and the 18. So the last rotation becomes between the 17 and the 18. The color is changed. See, if the rotation is done, then the color is changed. Then color is what? It is red, it becomes black and it becomes red. This is the color of black, this is the color black, this is the color red. After then again you have to check all these properties. And what I believe, applying these particular rules, you can make the final tree. So in my next slide, I am presenting the final answer after all these insertions. So I believe by using these steps, you can make this particular resultant tree very easily. If you facing any problem, then comment me. I will give solution. Okay. So the sum up of this particular lecture, in this particular lecture, we just brush up about the balance tree. After then we are watching, there are so many balance tree, and after then we are picking the topic is red black tree. After that we discussing properties about the RB tree, we picking different rotations are there, and finally we performing the insertion properties. So in my next video we will come with our next working in RB tree, which is deletion. So Jai Hind everyone.